Welcome to the Sleepless Universe. In this video, we'll explore some of the most mind-bending paradoxes that exist in our universe, thought experiments and scientific mysteries that challenge the very fabric of space, time, and reality itself. If you enjoy this kind of relaxing space content, I'd truly appreciate it if you left a like and subscribed. Now, sit back, relax, and enjoy this calming journey through the paradoxes of the cosmos. Twin paradox. Two identical twins share the same birthday, the same genetic code, and the same moment of birth. But according to Einstein's theory of relativity, if one twin travels to a distant star at nearly the speed of light while the other remains on Earth, they will age at dramatically different rates. When the traveling twin returns home, they will find their Earth-bound sibling has aged decades while they have aged only months or years. This counterintuitive scenario emerges from one of the most profound discoveries in physics. Time is not absolute. Instead, the passage of time depends on how fast you move through space. As objects approach the speed of light, time dilates, slowing to a crawl relative to stationary observers. What seems like science fiction is actually a fundamental property of our universe. The mathematics behind this phenomenon are surprisingly straightforward. Einstein's special relativity shows that time stretches by a factor that depends on velocity. At everyday speeds, this effect is negligible, but at 90% the speed of light, time passes more than twice as slowly for the traveler compared to someone at rest. Imagine the traveling twin journeying to Proxima Centauri, our nearest stellar neighbor, at 95% light speed. The trip takes just over 4 years from their perspective, but more than 8 years pass on Earth. Upon returning, the space-traveling twin has aged 8 years, while their Earth-bound sibling has aged 16 years. The paradox deepens when we consider that motion is relative. From the traveling twin's perspective, Earth appears to be moving away at tremendous speed, suggesting that the Earth-bound twin should be the one aging slowly. This apparent contradiction puzzled physicists for decades after Einstein first proposed his theory. The resolution lies in understanding that the situation is not truly symmetric. The traveling twin must accelerate to reach high speeds, decelerate upon arrival, accelerate again for the return journey, and finally decelerate when returning to Earth. These periods of acceleration break the symmetry and determine which twin experiences time dilation. During the acceleration phases, the traveling twin experiences forces similar to gravity. Einstein's general relativity reveals that gravity also affects the passage of time, with stronger gravitational fields causing time to slow down. The accelerating twin effectively experiences artificial gravity, contributing to their slower aging process. Experimental evidence for time dilation appears everywhere in modern physics. Particles created in cosmic ray collisions live longer than expected, because they travel at high speeds. Atomic clocks flown on airplanes run differently than identical clocks on the ground. GPS satellites must account for relativistic effects to maintain accuracy. The twin paradox extends beyond mere curiosity to practical considerations for future space exploration. Astronauts on missions to Mars experience measurable time dilation, though the effect amounts to mere milliseconds over typical mission durations. For interstellar travel, at significant fractions of light speed, the effects would be profound. From the traveling twin's perspective, the journey to distant stars becomes feasible through time dilation. What appears as a 100-year journey to Earth observers might be experienced as just a few years by high-speed travelers. This phenomenon could make exploration of the galaxy possible within human lifetimes, though the travelers would return to an Earth centuries older than when they departed. The paradox also raises philosophical questions about the nature of aging and identity. Which twin has lived longer when measured by biological processes versus external time? The answer depends on your frame of reference, highlighting how relativity challenges our intuitive understanding of simultaneous events. The twin paradox demonstrates that time itself is malleable, dependent on motion and gravity in ways that defy everyday experience. It reveals a universe where identical twins can have different histories, where space travel becomes time travel, and where the passage of time depends fundamentally on the path you choose through space-time. Length contraction, paradox. A meter stick rushing past you at nearly the speed of light appears shorter than an identical meter stick at rest. This length contraction represents one of the most startling predictions of Einstein's special relativity, suggesting that the fundamental properties of objects change depending on their motion relative to the observer. The phenomenon occurs because space and time are intimately connected in ways that contradict our everyday intuitions. As objects move faster through space, they contract along their direction of motion, while remaining unchanged in perpendicular dimensions. A speeding spacecraft becomes thinner in the direction of travel while maintaining its height and width. The mathematics reveal precise relationships between speed and contraction. At half the speed of light, objects shrink to about 87% of their rest length. At 90% light speed, they contract to just 43% of their original size. As velocity approaches the speed of light, length approaches zero. This creates apparent paradoxes that challenge our understanding of measurement and reality. Consider a long pole moving toward a barn at high speed. Due to length contraction, the pole appears short enough to fit entirely inside the barn, even though both pole and barn have identical rest lengths. Observers at rest can close both barn doors simultaneously with the pole inside. But from the pole's perspective, the situation reverses. The barn appears contracted while the pole maintains its proper length. From this viewpoint, the pole cannot possibly fit inside the shortened barn. This creates a paradox. Does the pole fit inside the barn or not? The resolution lies in understanding that simultaneity itself is relative. Events that appear simultaneous to one observer occur at different times for observers in relative motion. The barn doors that close simultaneously in the barn's reference frame close at different times from the pole's perspective. Length contraction affects more than abstract thought experiments. High-energy particles and accelerators experience significant contraction as they approach light speed. The circular paths they follow appear shorter from their own reference frames, affecting calculations of particle behavior and collision outcomes. Cosmic ray particles provide natural demonstrations of length contraction. Muons created high in Earth's atmosphere travel at speeds where length contraction becomes significant. From their perspective, the atmosphere appears much thinner than it does to ground-based observers, allowing them to reach the surface before decaying. The paradox extends to fundamental questions about the nature of solid objects. If length contraction is real, what happens to the atomic structure of compressed materials? Do the spaces between atoms shrink, or do the atoms themselves deform? The answer involves electromagnetic forces that also transform according to relativistic principles. Interestingly, length contraction cannot be directly measured by observers moving with the object. A ruler traveling at high speed appears normal to anyone moving with it. Only observers in different reference frames detect the contraction, making it a purely relative phenomenon. This relativity of measurement challenges traditional notions of objective reality. There is no absolute length, no universal meter stick that defines true size. Instead, length depends fundamentally on the relationship between observer and observed, making measurement an inherently relational process. Modern physics has confirmed length contraction through countless experiments with high-speed particles and precise atomic clocks. The effect represents more than mathematical curiosity. It reflects the fundamental structure of space-time itself. The length contraction paradox reveals that space, like time, is not the fixed backdrop we imagine. Instead, spatial dimensions respond dynamically to motion, stretching and compressing in ways that maintain the constancy of light speed across all reference frames. Understanding length contraction requires abandoning intuitive notions of absolute space and embracing a universe where measurement depends on motion. Objects have no single, true length, but instead possess different lengths for different observers, each equally valid within their own reference frame. Time dilation paradox. Time moves differently for everyone. This startling revelation from Einstein's theories of relativity shows that the steady tick of seconds we experience depends fundamentally on how fast we move and how deep we sit in gravitational fields. Time dilation creates scenarios where identical clocks can disagree about the passage of time, leading to paradoxes that challenge our most basic assumptions about temporal reality. Special relativity reveals that time slows down for objects moving at high speeds relative to an observer. A clock aboard a spacecraft, traveling at 90%, the speed of light runs slower than an identical clock on Earth. What the Earth clock measures as 1 hour, the spacecraft clock records as just 26 minutes. General relativity adds another layer of complexity by showing that gravity also affects time's passage. Clocks run slower in stronger gravitational fields, a phenomenon called gravitational time dilation. A clock at sea level runs slower than an identical clock on a mountaintop, though the difference amounts to mere nanoseconds over human lifetimes. These effects combine in counterintuitive ways. Satellites orbiting Earth experience both types of time dilation simultaneously. Their high orbital velocities cause special relativistic time dilation, making their clocks run slow. But their altitude places them in weaker gravitational fields, causing gravitational time dilation that makes their clocks run fast. The gravitational effect dominates, so satellite clocks run faster than Earth-based clocks. The Global Positioning System provides daily proof of time dilation's reality. GPS satellites must account for relativistic effects to maintain accuracy. Without these corrections, navigation errors would accumulate at rates of several miles per day, making the system useless for precise positioning. Particle accelerators demonstrate time dilation on a microscopic scale. Unstable particles that normally decay in microseconds live much longer when accelerated to high speeds. From the laboratory's perspective, time dilation extends the particles' lifetimes. From the particles' perspective, they experience normal lifetimes but traverse contracted distances. The paradox deepens when considering extreme environments. Near the event horizon of a black hole, gravitational time dilation becomes dramatic. An astronaut falling toward the black hole appears to slow down and freeze at the horizon from an outside observer's perspective. But the astronaut experiences time normally and quickly passes through the horizon. This creates information and paradoxes. If the astronaut appears frozen at the horizon forever, what happens to the information they carry? How can they simultaneously fall through the horizon and remain stuck at its boundary? These questions touch the deepest mysteries of quantum gravity and black hole physics. Time dilation also affects biological processes. Astronauts on the International Space Station age slightly slower than people on Earth due to their orbital velocity and reduced gravitational field. The effect is tiny but measurable with atomic clocks, amounting to microseconds over 6-month missions. The phenomenon raises philosophical questions about the nature of time itself. If time passes differently for different observers, which perspective represents real time? Einstein's answer was revolutionary. There is no universal time. Instead, each observer experiences their own proper time, equally valid within their reference frame. This multiplicity of times challenges causality and simultaneity. Events that appear simultaneous to one observer occur at different times for others. The future for one observer might be the past for another, creating complex relationships between cause and effect across different reference frames. Precision atomic clocks have verified time dilation to extraordinary accuracy. Experiments comparing clocks at different altitudes, different velocities, and different gravitational potentials consistently confirm Einstein's predictions. These tests push the boundaries of measurement precision while probing the fundamental nature of space-time. Time dilation represents more than scientific curiosity. It reveals that time itself is dynamic and malleable. Rather than flowing uniformly for all observers, time responds to motion and gravity in ways that make each journey through space-time unique. The universe operates according to principles where time becomes personal, where every clock tells its own story of temporal passage. Simulation Paradox. The world around you feels undeniably real. You see colors, feel textures, experience emotions, and navigate through what appears to be physical space filled with solid objects. But philosopher Nick Bostrom proposed a startling possibility. It might be more likely that you exist as simulated consciousness within an advanced computer program than as a biological being in a fundamental reality. The simulation hypothesis emerges from considering the potential computational power of future civilizations. If technological progress continues, advanced societies might develop computers capable of running detailed simulations, containing conscious beings who believe they inhabit real worlds. These simulated people would experience thoughts, emotions, and sensations indistinguishable from those of beings in base reality. The mathematical argument is compelling. If even a small fraction of advanced civilizations run ancestor simulations or other detailed reality simulations, the number of simulated conscious beings would vastly exceed the number of non-simulated ones. By pure probability, any randomly selected conscious being would more likely be simulated than real. This creates the simulation paradox. The more successful we become at creating realistic simulations, the more likely it becomes that we ourselves are simulated. Advanced civilizations might run millions of detailed historical simulations, each containing billions of conscious individuals who never suspect their reality is artificial. Evidence supporting the simulation hypothesis appears in unexpected places. The universe seems to follow mathematical laws that could represent computational rules. Physical constants appear fine-tuned for complexity, perhaps because simulated realities require parameters that allow interesting phenomena to emerge. Quantum mechanics might represent computational shortcuts that avoid calculating unobserved details. The paradox deepens when considering nested simulations. Simulated beings might develop their own computing technology and create their own simulations, leading to multiple layers of artificial reality. You might exist in a simulation run by simulated beings who themselves exist in another simulation, creating potentially infinite recursive levels of reality. Some interpretations suggest we might detect evidence of our simulated nature. Computational limitations might manifest as fundamental physical constants, pixel-like structure at the smallest scales, or glitches in the program that appear as unexplained phenomena. The universe's apparent quantization of energy, space, and time might reflect underlying computational architecture. The simulation hypothesis raises profound questions about consciousness and identity. If you are simulated, are your experiences less real than those of non-simulated beings? Does it matter whether your thoughts arise from biological neurons or digital processes? Perhaps consciousness itself is substrate independent, making simulated and biological minds equally valid. Religious and philosophical implications abound. The beings running our simulation might appear godlike from our perspective, possessing power to create and destroy worlds, observe all events, and potentially intervene in simulated histories. This technological transcendence might explain experiences attributed to divine intervention or supernatural phenomena. The paradox also suggests practical considerations. If we are simulated, should we behave differently? Perhaps the simulation's purpose is to observe how conscious beings develop morally and technologically. Our choices might influence whether the simulation continues or whether we are considered worthy of advancement to higher reality levels. Critics argue that the simulation hypothesis is unfalsifiable and therefore unscientific. Others question whether consciousness can truly emerge from computational processes or whether simulating consciousness requires resources equivalent to the consciousness being simulated, making large-scale ancestor simulations impractical. Recent developments in virtual reality, artificial intelligence, and quantum computing make the simulation hypothesis increasingly relevant. As our own simulations become more sophisticated, we approach the technological threshold where creating convincing artificial worlds becomes feasible. The simulation paradox forces us to question the nature of reality itself. Perhaps the distinction between simulated and non-simulated existence is meaningless if both can support consciousness and meaningful experience. Whether we inhabit base reality or exist as patterns in some cosmic computer, our experiences remain valid and our choices continue to matter within the framework of whatever reality we occupy. Grandfather Paradox. Imagine traveling back in time to meet your grandfather as a young man, decades before your parent was born. In a moment of poor judgment or accident, you prevent your grandfather from meeting your grandmother. Without their meeting, your parent is never born, which means you are never born. But if you are never born, how could you have traveled back in time to cause this change in the first place? This grandfather paradox represents the most famous logical puzzle associated with time travel, highlighting the seemingly impossible contradictions that arise when cause and effect form closed loops. The paradox challenges our understanding of causality, free will, and the fundamental nature of time itself. The problem extends beyond family relationships to any scenario where time travelers alter past events that led to their own existence or ability to travel. Preventing a war that motivated your invention of time travel, stopping the accident that inspired your scientific career, or simply changing any event in the causal chain leading to your journey creates similar paradoxes. Several theoretical solutions attempt to resolve this logical contradiction. The Novikov self-consistency principle suggests that the universe somehow prevents paradoxes from occurring. In this framework, any actions you take in the past were always part of history. You cannot change the past because your interventions were already factored into the timeline. This interpretation implies that free will in the past is constrained by consistency requirements. If you travel back intending to prevent your grandfather's meeting with your grandmother, circumstances will somehow ensure the meeting occurs anyway. Perhaps your interference actually causes them to meet, or your presence creates the exact conditions necessary for their romance. The many worlds interpretation offers a different resolution by proposing that changing the past creates alternate timelines rather than paradoxes. When you prevent your grandfather's meeting with your grandmother, you create a new branch of reality where you are never born, but you originated from a different timeline where the meeting did occur, allowing your continued existence even as you alter this alternate past. This solution suggests that time travel might be possible, but would transport you to parallel universes rather than your own past. You could witness and influence alternate versions of historical events, but could never return to your original timeline. Every change would create new branches, making time travel a one-way journey into increasingly divergent realities. Some theories propose that time travel to the past is simply impossible, not because of technological limitations, but because of fundamental physical laws that prevent closed time-like curves. The universe might possess a chronology protection mechanism that prevents the formation of causal loops through quantum effects or other physical processes. The grandfather paradox also highlights the relationship between time travel and information. If you travel to the past with knowledge of future events, where did that information originate? This creates bootstrap paradoxes where information appears to have no ultimate source, existing in closed causal loops that seem to violate principles of logic and causality. Quantum mechanics adds another layer of complexity to time travel paradoxes. Some interpretations suggest that quantum uncertainty might resolve grandfather paradox situations by creating probabilistic outcomes that prevent definitive paradoxes while allowing limited alterations to past events. The paradox extends to questions about personal identity across time. If you prevent your own birth, do you cease to exist, fade away gradually, or continue existing as an anomaly outside normal causality? Different time travel theories predict different outcomes for the unfortunate time traveler caught in a grandfather paradox situation. Modern physics generally suggests that macroscopic time travel to the past faces insurmountable obstacles. Though exotic scenarios involving wormholes, cosmic strings, or rotating massive objects might theoretically permit limited forms of temporal displacement, these solutions typically require negative energy densities or other conditions that may be physically impossible. The grandfather paradox remains one of the most enduring puzzles in discussions of time travel, serving as a logical boundary that constrains theoretical possibilities and highlights the deep connections between causality, consciousness, and the fundamental structure of temporal reality. Bootstrap Paradox. In the labyrinthine corridors of theoretical physics, few concepts challenge our understanding of causality as profoundly as the Bootstrap Paradox. This enigmatic puzzle asks a deceptively simple question: can information or objects exist without ever having been created? The paradox emerges most clearly in scenarios involving closed time-like curves, where cause and effect become so intertwined that they form an endless loop with no discernible beginning or end. The Bootstrap Paradox takes its name from the impossible feat of lifting oneself by pulling on one's own bootstraps, a metaphor that perfectly captures the self-referential nature of this temporal conundrum. In physics, the paradox manifests when information travels backward through time and becomes the very source of its own existence, creating a causal loop that appears to violate our fundamental understanding of how the universe operates. Consider a hypothetical scenario where a physicist receives the blueprints for a time machine from their future self, builds the device, travels back in time, and gives those same blueprints to their younger self. The question becomes unavoidable. Where did the information for building the time machine originally come from? The blueprints seem to exist in an eternal loop, never actually created but somehow always present in the timeline. The paradox becomes even more perplexing when we examine it through the lens of information theory. In our universe, information appears to be a conserved quantity, neither created nor destroyed, but merely transformed from one form to another. The Bootstrap Paradox seems to violate this fundamental principle by suggesting that information can exist in a closed loop without any external source, appearing to emerge from nothing and sustain itself through temporal recursion. Einstein's general theory of relativity permits the existence of closed time-like curves under certain extreme conditions, such as near-rotating black holes or in exotic spacetime geometries involving negative energy densities. These mathematical solutions to Einstein's field equations allow for the theoretical possibility of traveling backward through time, creating the conditions necessary for bootstrap paradoxes to occur in our universe. Quantum mechanics introduces additional complexity through the principle of quantum consistency. Some interpretations suggest that quantum effects might prevent paradoxes by ensuring that only self-consistent timelines can exist. In this view, the universe somehow conspires to prevent contradictory information loops, allowing only those bootstrap scenarios that maintain logical consistency across all temporal iterations. The many worlds interpretation of quantum mechanics offers another perspective, suggesting that time travel might create branching timelines rather than closed loops, with each iteration occurring in a separate parallel universe. This approach eliminates the paradox by removing the requirement for true temporal loops, but raises equally profound questions about the nature of reality and information conservation across multiple universes. Novikov's self-consistency principle provides a potential resolution by proposing that the laws of physics somehow prevent paradoxes from occurring. According to this principle, if time travel is possible, then only those events that create self-consistent timelines can actually take place in reality. The Bootstrap Paradox ultimately challenges our most basic assumptions about the nature of existence, causality, and the arrow of time, forcing us to confront the possibility that reality might be far stranger and more self-referential than our everyday experience suggests. Light clock paradox. Among the most elegant demonstrations of special relativity's counterintuitive nature, the light clock paradox reveals how the fundamental nature of time itself changes depending on one's frame of reference. This thought experiment involves a simple device that measures time using light pulses bouncing between mirrors, exposing the profound reality that there is no universal clock ticking away at the same rate throughout the universe. Instead, time dilates and contracts based on relative motion, creating a paradox that challenges our deepest intuitions. The light clock consists of two parallel mirrors separated by a fixed distance, with a pulse of light bouncing back and forth between them. Each round trip of the light pulse represents one tick of this temporal measuring device. To an observer at rest, relative to the clock, the light travels in straight lines between the mirrors, covering a predictable distance at the speed of light and creating a steady rhythm that can serve as a reliable timekeeper. The paradox emerges when the light clock moves at high velocity relative to an outside observer. From this perspective, the light pulse no longer travels in straight lines between the mirrors. Instead, it follows a diagonal zigzag path, traveling a greater distance with each tick, while maintaining the same speed of light. Since the light covers more distance at the same speed, each tick takes longer from the external observer's viewpoint. This seemingly simple observation leads to a profound conclusion. Moving clocks run slower than stationary ones, a phenomenon known as time dilation. The effect becomes more pronounced as relative velocity approaches the speed of light, with time appearing to slow dramatically for objects moving at near light speeds. This is not merely an illusion or measurement error. It represents a fundamental property of spacetime itself. The paradox deepens when we consider the principle of relativity, which states that all inertial reference frames are equally valid. From the perspective of someone moving with the light clock, they are at rest, and it is the external observer who is moving. By the same logic, the moving observer's clock should appear to run slowly from the light clock's reference frame. This creates an apparently contradictory situation, where each observer sees the other's clocks running slowly. The resolution lies in understanding that both observations are simultaneously correct within their respective reference frames. There is no absolute standard of time that determines which clock is really running slower. Each observer experiences their own proper time normally, while observing other reference frames as time dilated. This mutual time dilation represents one of the most counterintuitive aspects of special relativity. The light clock paradox becomes even more complex when acceleration is introduced. If one of the observers accelerates to match the velocity of the other, they can directly compare their clocks and resolve any apparent contradictions. The observer who experienced acceleration will find that their clock has fallen behind, demonstrating that acceleration breaks the symmetry between reference frames. Experimental verification has been achieved through high-precision measurements using atomic clocks on fast-moving aircraft and satellites. These experiments consistently confirm Einstein's predictions, showing that moving clocks indeed run slower by exactly the predicted amount. The global positioning system relies on precise corrections for relativistic time dilation to maintain its extraordinary accuracy. The light clock paradox ultimately reveals that time is not the fixed, universal constant that everyday experience suggests, but rather a dynamic dimension of spacetime that responds to motion in ways that continue to challenge our understanding of reality's fundamental structure. Gravitational lensing paradox. In the vast cosmic theater where light from distant stars travels across billions of years to reach our telescopes, one phenomenon challenges our basic understanding of how light behaves. Gravitational lensing, the bending of light around massive objects, presents a fundamental paradox that puzzled physicists for decades. How can light, which has no mass, be deflected by gravitational fields that supposedly only affect massive particles? This apparent contradiction between the massless nature of photons and their observed interaction with gravity reveals deep truths about the nature of spacetime itself. Classical physics, built upon Newton's understanding of gravity as a force between massive objects, provides no mechanism for light to interact gravitationally. In the Newtonian framework, gravity affects only objects with mass, pulling them towards centers of gravitational attraction with a force proportional to their mass. Since light consists of massless photons, classical theory predicts that gravitational fields should have no effect on light's trajectory, allowing photons to travel in perfectly straight lines regardless of nearby massive objects. The first hints that gravity might affect light came from Einstein's principle of equivalence, which states that gravitational acceleration is indistinguishable from any other form of acceleration. If someone in a windowless elevator cannot tell whether they're accelerating upward or experiencing downward gravitational pull, then light beams should behave identically in both situations. Since accelerating elevators bend light beams, Einstein reasoned that gravitational fields must also bend light. Einstein's general theory of relativity revolutionized our understanding by revealing that gravity is not a force at all, but rather the curvature of spacetime itself. Massive objects warp the fabric of spacetime, creating curved paths that all objects, including massless photons, must follow. Light doesn't bend because gravity pulls on it, but because space itself is curved, forcing light to follow the shortest possible path through curved geometry. The mathematical description involves geodesics, the shortest paths through curved spacetime. Just as a straight line represents the shortest distance between 2 points on a flat surface, geodesics represent the straightest possible paths through curved spacetime. When light travels near massive objects, it follows these curved geodesics, appearing to bend from the perspective of distant observers while actually traveling in the straightest line possible through the warped geometry. The first experimental confirmation came during the solar eclipse of 1919, when Arthur Eddington measured the apparent positions of stars near the sun's edge. The observations showed that starlight was deflected by exactly the amount Einstein's theory predicted, twice the deflection that Newtonian gravity would produce if light somehow had mass. This historic measurement provided crucial evidence for general relativity and revolutionized our understanding of gravity. Modern astronomy has revealed gravitational lensing as a widespread phenomenon throughout the universe. Galaxy clusters act as cosmic magnifying glasses, distorting and amplifying the images of more distant galaxies behind them. These gravitational telescopes allow astronomers to observe objects that would otherwise be too faint to detect, providing windows into the most distant reaches of the observable universe. Strong gravitational lensing creates multiple images of the same distant object, arranged in patterns that depend on the precise alignment between source, lens, and observer. In perfect alignments, the lensed object appears as a bright ring called an Einstein ring, surrounding the lensing mass. These phenomena provide powerful tools for measuring the masses of distant galaxies and galaxy clusters. The gravitational lensing paradox ultimately reveals that our intuitive understanding of space, time, and motion breaks down in the presence of strong gravitational fields, demonstrating that the universe operates according to geometric principles far more subtle and beautiful than everyday experience suggests. Spacetime Curvature Paradox. The most profound mystery in Einstein's general theory of relativity lies not in its complex mathematics or exotic predictions, but in a conceptual puzzle that strikes at the heart of reality itself. How can nothing be curved? The spacetime curvature paradox emerges from the counterintuitive notion that empty space, the apparent vacuum that exists between matter, possesses geometric properties that can bend, stretch, and warp in response to mass and energy. This paradox challenges our most basic intuitions about the nature of nothingness and forces us to reconceptualize the very stage upon which all physical phenomena unfold. In everyday experience, curvature requires something substantial to be curved. A bent road, a warped piece of metal, or a curved line drawn on paper all involve the deformation of material objects that possess tangible existence. The concept of curvature seems meaningless without some underlying substance that can be shaped or distorted. Yet Einstein's theory demands that we accept the possibility that space itself, the seemingly empty arena in which objects move, can be curved even in regions completely devoid of matter. The paradox becomes even more perplexing when we consider that classical physics treated space as an absolute, unchanging backdrop against which physical events occur. Newton's conception of space was that of a fixed, eternal stage that remained unaffected by the actors performing upon it. Time, similarly, was viewed as a universal constant, flowing uniformly throughout the universe, independent of any physical processes. The notion that this backdrop could itself be dynamic and responsive to physical conditions seemed completely absurd. Einstein's breakthrough came from recognizing that space and time are not separate entities but form a unified four-dimensional manifold called spacetime. This spacetime continuum possesses geometric properties that can be described mathematically using the tools of differential geometry, the same mathematics used to describe curved surfaces like spheres or saddles. Mass and energy act as sources of spacetime curvature, warping the geometry of the continuum in their vicinity. The curvature of spacetime manifests in observable phenomena that we interpret as gravitational effects. Objects follow geodesics, the straightest possible paths through curved spacetime, which appear as curved trajectories to observers using Euclidean geometry. A planet orbiting the Sun is actually traveling in a straight line through spacetime that has been curved by the Sun's mass, creating the illusion of a gravitational force pulling the planet toward the center. The mathematical description of spacetime curvature involves tensors, mathematical objects that describe how geometric properties change from point to point throughout the continuum. The Einstein field equations relate the curvature tensor at each point in spacetime to the energy-momentum tensor, which describes the distribution of matter and energy at that location. These equations reveal that spacetime curvature is not merely correlated with matter, but is actually created by it. Experimental evidence for spacetime curvature comes from numerous sources, including the precession of Mercury's orbit, the bending of light around massive objects, and the detection of gravitational waves. Each of these phenomena can be understood as manifestations of curved spacetime geometry, rather than the effects of mysterious forces acting through empty space. The recent direct detection of gravitational waves has provided perhaps the most dramatic confirmation of spacetime's dynamic nature. The paradox deepens when we consider what spacetime curvature means at the quantum level. Quantum field theory suggests that even empty space is filled with quantum fluctuations, virtual particles that briefly appear and disappear according to the uncertainty principle. These quantum effects contribute to the energy content of space itself, potentially affecting its geometric properties in ways that our current theories cannot fully describe. Black holes represent the most extreme examples of space-time curvature, where the geometry becomes so severely warped that it creates regions from which nothing, not even light, can escape. Near a black hole's event horizon, space-time curvature becomes so intense that tidal forces would stretch any material object to the breaking point, demonstrating the very real physical consequences of geometric distortion. The space-time curvature paradox ultimately forces us to abandon our intuitive notions of space as an empty container and time as a universal flow, replacing them with a dynamic, responsive medium that participates actively in the physical processes it contains, challenging us to reconceptualize the very nature of existence itself. White hole paradox. In the elegant mathematical symmetries of Einstein's general relativity lies a theoretical construct so bizarre and elusive that it has never been observed despite decades of searching: the white hole. These hypothetical objects represent the time-reversed mirror image of black holes, regions of space-time that violently expel matter and energy rather than consuming them. The white hole paradox asks a fundamental question that has puzzled physicists for generations. If the mathematics of general relativity predicts both black holes and white holes with equal validity, why does our universe seem to contain only one type of these extreme gravitational phenomena? The mathematical foundation for white holes emerges directly from the same solutions to Einstein's field equations that describe black holes. When the Schwarzschild solution is extended to cover all possible regions of spacetime, it reveals not just the familiar black hole with its event horizon that prevents escape, but also a white hole region where an event horizon prevents entry. While nothing can escape from inside a black hole's event horizon, nothing can enter a white hole from outside its boundary. The symmetry between black and white holes runs deeper than mere mathematical curiosity. If we imagine filming a black hole consuming matter and then playing the footage in reverse, we would see a white hole expelling that same matter. This time reversal symmetry suggests that white holes should be as fundamental to the structure of spacetime as their better-known counterparts. Yet observational astronomy has found no convincing evidence for their existence anywhere in the observable universe. White holes would represent the ultimate cosmic fountains, spontaneously erupting matter and energy into the surrounding spacetime without any apparent source or cause. Unlike black holes, which gradually grow by accreting material from their surroundings, white holes would steadily diminish as they expel their contents, eventually evaporating completely when their internal mass energy is exhausted. This process would occur in reverse temporal order compared to black hole formation and growth. The paradox becomes more acute when we consider that many astrophysical processes that create black holes should, by symmetry arguments, also create white holes. Stellar collapse that forms a black hole involves matter crossing an event horizon and disappearing from the observable universe. The time-reversed process would involve matter spontaneously appearing at a white hole's event horizon and expanding outward, yet we observe no such phenomena, despite their theoretical inevitability. Some cosmologists have speculated that the Big Bang itself might have been a white hole event, with the entire observable universe emerging from a primordial white hole that existed before time began. In this interpretation, the initial singularity that gave birth to space, time, and matter represents the interior of a white hole that exploded outward to create everything we observe. This model provides an intriguing alternative to traditional Big Bang cosmology, though it raises as many questions as it answers. The thermodynamic properties of white holes present additional paradoxes that challenge our understanding of entropy and information. Black holes are known to possess temperature and entropy proportional to their surface area, gradually evaporating through Hawking radiation, while increasing the total entropy of the universe. White holes would presumably have negative entropy, spontaneously decreasing the universe's disorder by organizing matter into complex structures without any external input. The instability of white holes provides a potential explanation for their absence from the observable universe. Unlike black holes, which are stable against small perturbations, white holes appear to be fundamentally unstable. Any matter that approaches a white hole's event horizon would cause the entire structure to collapse, potentially transforming it into a black hole or causing it to explode catastrophically. Recent research into the black hole information paradox has led some physicists to speculate that black holes might eventually transition into white holes through quantum effects, providing a mechanism for information to escape from behind event horizons. These black-to-white hole transitions remain highly speculative, but offer potential resolutions to some of the deepest paradoxes in theoretical physics. The white hole paradox ultimately highlights the deep mysteries that remain hidden within the mathematical structure of general relativity, challenging us to understand why the universe seems to prefer one temporal direction over another, and why cosmic asymmetries exist despite the fundamental symmetries of physical law. Anthropic Principle Paradox. In the vast cosmic theater of physical constants and fundamental forces, a profound question emerges. Do we exist because the universe allows life, or does the universe appear fine-tuned for life simply because we're here to observe it? The Anthropic Principle Paradox represents one of the most philosophically charged debates in modern cosmology, forcing us to confront the relationship between observation and reality. The paradox arises from the observation that our universe appears exquisitely fine-tuned for life. The fundamental constants of nature, gravity's strength, electromagnetic force, electron mass, and dozens of other parameters, all fall within incredibly narrow ranges permitting atoms, stars, planets, and life. Change any values by tiny amounts, and the universe becomes a sterile wasteland incapable of supporting complexity. Consider the delicate balance required for stellar nucleosynthesis, the process by which stars forge heavy elements essential for life. If the strong nuclear force were slightly weaker, hydrogen nuclei could never fuse to form helium, and stars would never ignite. If slightly stronger, hydrogen would burn so rapidly that stars would exhaust their fuel in millions rather than billions of years, providing insufficient time for biological evolution. The weak anthropic principle offers a seemingly simple resolution. We observe a life-friendly universe because we could not exist in any other type. This principle argues that our existence as observers naturally selects for a universe compatible with our presence, making the apparent fine-tuning an inevitable consequence of observation, bias, rather than cosmic design. However, this explanation raises deeper questions about the nature of reality and observation. If our existence determines what we can observe, does this mean that unobserved realities are somehow less real? The paradox becomes particularly acute when we consider that our observations seem to influence the fundamental nature of the cosmos we're trying to understand objectively. The strong anthropic principle takes a more controversial stance, suggesting that the universe must possess properties that allow life to develop within it at some stage. This formulation implies that consciousness and observation play fundamental roles in determining physical reality, echoing interpretations of quantum mechanics that assign special significance to the act of measurement. Multiverse theories provide another perspective by proposing that our universe is just one of countless universes with different physical constants and laws. In this vast ensemble, most universes would indeed be sterile, but observers like ourselves naturally find themselves in the rare universes capable of supporting life. The apparent fine-tuning becomes a selection effect rather than evidence for design. The Anthropic Principle Paradox ultimately forces us to confront the deepest questions about the relationship between mind and cosmos, challenging us to understand whether we are passive observers of an independent reality or active participants in creating the universe we experience. Low Entropy Paradox. Among the most puzzling aspects of our universe's origin lies a mystery that challenges our understanding of thermodynamics and cosmic evolution. Why did the universe begin in such an incredibly ordered, low-entropy state? The low-entropy paradox emerges from the observation that the Big Bang appears to have started with matter and energy arranged in an almost impossibly organized configuration, creating the potential for billions of years of increasing complexity and structure formation. The second law of thermodynamics tells us that entropy, or disorder, always increases in isolated systems. This principle governs everything from melting ice to the universe's eventual heat death. Yet tracing cosmic evolution backward reveals a profound puzzle. The universe appears to have emerged from extraordinarily low entropy, perfectly positioned to evolve into the complex, structured cosmos we observe. In the first moments after the Big Bang, matter and energy were distributed with remarkable uniformity throughout space. The cosmic microwave background radiation reveals temperature variations of less than 1 part in 100,000 across the entire observable universe. This near-perfect smoothness represents an incredibly ordered initial state, far from the maximum entropy configuration that thermodynamics would typically predict. The paradox becomes more striking when we consider the astronomical number of possible ways the universe's initial energy could have been arranged. The overwhelming majority of these configurations would have produced chaotic, structureless universes incapable of forming galaxies, stars, or planets. The probability of randomly achieving the low-entropy initial conditions required for our structured universe appears vanishingly small. Statistical mechanics provides a framework for understanding entropy in terms of the number of microscopic arrangements that correspond to a given macroscopic state. A low-entropy state has few possible microscopic configurations, while high-entropy states have vastly more arrangements available. The universe's initial low-entropy condition implies that its fundamental constituents were organized in one of relatively few specific ways. The paradox deepens when we consider that the universe's current complexity and structure directly result from its initial simplicity. Galaxies, stars, and life itself emerged through gravitational collapse and thermodynamic processes that were only possible because the early universe was so smoothly distributed. Without this initial low-entropy state, gravity would have had no small density fluctuations to amplify into the cosmic structures we observe. Some cosmologists propose that cosmic inflation might explain the low initial entropy. During inflation, quantum fluctuations could have been stretched to cosmic scales, creating the nearly uniform distribution of matter and energy we observe. However, this explanation merely pushes the paradox back one step. What created the special conditions necessary for inflation to begin? The low-entropy paradox remains one of cosmology's most profound unsolved problems, touching on fundamental questions about the nature of time, causality, and the origin of cosmic order. Baryonic Matter Paradox. In the fundamental particle zoo that emerged from the Big Bang's primordial fires, a puzzling asymmetry challenges our understanding of cosmic evolution. Why does our universe consist almost entirely of ordinary matter, protons, neutrons, and electrons, rather than the exotic particles that theories predict should be equally abundant? The Baryonic Matter Paradox asks why these familiar constituents of atoms dominate the cosmic inventory, when more fundamental theories suggest that far stranger forms of matter should be equally prevalent. The Standard Model predicts the early universe should have produced equal quantities of matter and antimatter, plus exotic particles interacting weakly with ordinary matter. Yet observations reveal a cosmos dominated by familiar baryonic matter, protons and neutrons forming atomic nuclei, with antimatter virtually absent and exotic particles relegated to invisible dark matter outweighing visible matter 5-1. The matter-antimatter asymmetry represents one of the most striking aspects of the Baryonic paradox. In the first moments after the Big Bang, high-energy particle interactions should have created equal amounts of matter and antimatter. These particles should have promptly annihilated each other, leaving behind only photons and perhaps some stable exotic particles. Instead, we observe a universe where matter survived and antimatter disappeared. Sakharov's conditions outline the theoretical requirements for generating matter-antimatter asymmetry, baryon number violation, charge and parity violation, and departure from thermal equilibrium. While the Standard Model contains mechanisms that satisfy these conditions, they appear insufficient to explain the observed asymmetry. The process must have been extraordinarily efficient, converting a tiny initial imbalance into the complete dominance of matter. The abundance of light elements provides another puzzle within the Baryonic paradox. Big Bang nucleosynthesis successfully predicts the observed abundances of hydrogen, helium, and lithium based on the density of baryonic matter in the early universe. However, this same calculation suggests that baryonic matter should constitute only about 5% of the universe's total mass energy, with the remainder consisting of mysterious dark matter and dark energy. Supersymmetry and other extensions to the Standard Model predict numerous exotic particles that should have been produced in the early universe and could still exist today. These theories suggest that for every ordinary particle, there should be corresponding supersymmetric partners with different properties but similar abundances. Yet, despite decades of searching with increasingly powerful particle accelerators, none of these predicted particles have been detected. The stability of protons adds another dimension to the paradox. Many grand unified theories predict that protons should decay over extremely long timescales, gradually converting all atomic nuclei into lighter particles and energy. The fact that protons appear to be perfectly stable, or at least have decay times far longer than current theoretical predictions, suggests that our understanding of particle physics remains fundamentally incomplete. The Baryonic Matter Paradox ultimately highlights the gaps in our understanding of particle physics and cosmology, challenging us to explain why the universe chose familiarity over exoticism in determining the fundamental constituents of cosmic structure. Cosmic Horizon Paradox. In the vast expanse of the observable universe, a fundamental puzzle emerges from the cosmic microwave background radiation. How can regions of space separated by distances greater than light could have traveled since the Big Bang display nearly identical temperatures and properties? The Cosmic Horizon Paradox, also known as the Horizon Problem, reveals an apparent violation of the principle that no information or influence can travel faster than light. The paradox becomes apparent examining the cosmic microwave background, the Big Bang's afterglow filling the entire observable universe. This radiation exhibits remarkably uniform temperature of 2.725 Kelvin in all directions, with variations less than 1 part in 100,000 across the entire sky. Such uniformity suggests these distant regions were once in thermal equilibrium, exchanging energy to reach identical temperatures. However, the geometry of spacetime since the Big Bang appears to make such thermal equilibrium impossible. Light from opposite sides of the observable universe has been traveling toward us for approximately 13.8 billion years, meaning these regions are separated by roughly 27.6 billion light-years, accounting for cosmic expansion. At the time, the cosmic microwave background was emitted, when the universe was only 380,000 years old. These regions were already separated by distances far exceeding what light could have traveled. The paradox emerges from the concept of particle horizons, which define the maximum distance that light or any causal influence could have traveled since the beginning of time. Regions beyond each other's particle horizons should have no way to coordinate their properties or reach thermal equilibrium. Yet, the cosmic microwave background suggests that the entire observable universe was once in thermal contact. Standard Big Bang cosmology without inflation predicts that the observable universe should contain approximately 100,000 independent regions that were never in causal contact with each other. Each region should have evolved independently, developing its own temperature and density based on local initial conditions. The fact that we observe such remarkable uniformity across all these regions suggests something is fundamentally wrong with our understanding of early cosmic evolution. The paradox becomes even more puzzling when we consider that the uniformity must have been established very early in cosmic history, long before the mechanisms that typically drive systems toward equilibrium could have operated. Thermal equilibrium usually results from many interactions between particles over extended periods, but the cosmic microwave background's uniformity appears to have been present from the very beginning. Cosmic inflation provides the most widely accepted solution to the Horizon Paradox, by proposing that the universe underwent a period of exponential expansion in its earliest moments. During inflation, a tiny region of space that was initially in causal contact expanded by an enormous factor, stretching far beyond the observable universe we see today. This process would ensure that all regions we can observe today originated from a single, causally connected patch of space. The inflationary solution works by fundamentally changing the relationship between distance and time in the early universe. Instead of the steady expansion described by standard Big Bang models, inflation involves a period where space expanded much more rapidly than light could travel through it. The cosmic horizon paradox ultimately reveals the profound challenges involved in understanding the universe's earliest moments, highlighting how observations of cosmic uniformity can reveal fundamental insights about the nature of space, time, and causality. Technosignature Paradox. In the cosmic search for intelligence beyond Earth, a profound silence challenges our assumptions about technological civilizations. Despite decades of systematic searching and increasingly sophisticated detection methods, we have found no convincing evidence of advanced alien technologies anywhere in the observable universe. The Technosignature Paradox asks why the cosmos appears devoid of the technological artifacts, communications, or megastructures that we might expect from civilizations with millions or billions of years of technological development ahead of our own. The paradox becomes striking considering the vast scales of time and space available for technological civilizations to develop and spread throughout the galaxy. Our Milky Way is approximately 10 billion years old, providing ample time for intelligent species to evolve, develop technology, and expand across stellar distances. Even with conservative interstellar travel assumptions, a single technological civilization could theoretically colonize the entire galaxy within a few million years. The search for extraterrestrial intelligence has employed increasingly powerful radio telescopes and sophisticated analysis techniques to scan the sky for artificial signals that might indicate the presence of technological civilizations. These searches have examined millions of star systems across a wide range of frequencies, looking for patterns that could not be produced by natural astrophysical processes. Yet, despite this extensive effort, we have detected no confirmed technosignatures of any kind. The absence of detectable megastructures presents another dimension of the paradox. Advanced civilizations with access to stellar-scale energy sources might be expected to construct massive engineering projects visible across interstellar distances. Dyson spheres, ring worlds, or other large-scale structures could harness the energy output of entire stars, creating distinctive infrared signatures that our telescopes should be able to detect. Surveys of millions of galaxies have found no evidence of such constructions. The paradox deepens when we consider that technological civilizations might naturally expand their capabilities exponentially over time. Digital technologies, artificial intelligence, and nanotechnology could enable rapid growth in computational power, energy utilization, and construction capabilities. Such exponential growth would quickly lead to technological capabilities far beyond our current imagination, making their detection signatures potentially obvious across cosmic distances. One possible resolution involves the concept of the Great Filter, a hypothetical evolutionary bottleneck that prevents most life from developing into detectable technological civilizations. This filter could operate at any stage of development, from the emergence of life itself to the development of intelligence or the transition to technological sophistication. If the filter lies behind us, it might explain why technological civilizations are extremely rare. Alternative explanations suggest that advanced civilizations might deliberately avoid producing detectable signatures, either to preserve their privacy or to avoid attracting potentially hostile attention from other technological species. This dark forest hypothesis proposes that the universe might be filled with hidden civilizations that remain silent to avoid detection by potentially dangerous neighbors. The possibility of technological transcendence offers another perspective on the paradox. Sufficiently advanced civilizations might develop technologies that move beyond physical manipulation of matter and energy, focusing instead on information processing, virtual reality, or other activities that produce no detectable signatures. The Technosignature Paradox ultimately forces us to confront fundamental questions about the nature of intelligence, technology, and cosmic evolution, challenging our assumptions about the inevitability of technological development and the long-term survival of advanced civilizations. The Technosignature Paradox ultimately forces us to confront fundamental questions about the nature of intelligence, technology, and cosmic evolution, challenging our assumptions about the inevitability of technological development and the long-term survival of advanced civilizations. Matter-Antimatter Annihilation Paradox. In the earliest moments of our universe, something extraordinary happened that allowed you to exist today. According to our understanding of particle physics, matter and antimatter should have been created in equal amounts during the Big Bang. These cosmic twins are identical in every way except for their opposite charges, and when they meet, they annihilate each other completely, converting into pure energy. This creates a profound puzzle. If equal amounts of matter and antimatter were born together, they should have completely destroyed each other within the first fraction of a second after the Big Bang. The universe should have been left as nothing but a sea of photons, with no stars, no planets, and certainly no life. Yet here we are, surrounded by a cosmos rich with matter. The solution lies in a subtle but crucial asymmetry. For every billion pairs of matter and antimatter particles that annihilated each other, there was just one extra matter particle left behind. This tiny imbalance, known as baryogenesis, is responsible for everything we see around us. Every atom in your body, every star in the night sky, and every galaxy stretching across the cosmic web exists because of this minuscule difference. Scientists have discovered that certain fundamental processes favor matter over antimatter, though only by the smallest of margins. Deep within particle accelerators, researchers observe particles called mesons that decay slightly more often into matter than antimatter. This preference, while incredibly small, becomes significant when multiplied across the trillions upon trillions of particles present in the early universe. The cosmic microwave background radiation that fills space today carries the afterglow of this ancient annihilation event. When matter and antimatter destroyed each other, they released tremendous amounts of energy that still permeates the universe, now cooled to just a few degrees above absolute zero. This gentle warmth is the fossil evidence of the greatest destruction event in cosmic history. What makes this paradox even more intriguing is that antimatter still exists today, though in much smaller quantities. Cosmic rays striking our atmosphere occasionally produce antiparticles, and some radioactive elements naturally emit positrons, the antimatter counterpart of electrons. Scientists can even create antimatter in laboratories, though storing it remains an extraordinary challenge since it annihilates instantly upon contact with ordinary matter. The matter-antimatter asymmetry remains one of the most important unsolved problems in cosmology. While we can observe the effects and measure the imbalance, the complete explanation for why our universe chose matter over antimatter continues to elude us. This fundamental asymmetry not only allowed the universe to exist, but set the stage for the complex chemistry that would eventually give rise to life itself. The implications extend beyond our immediate cosmic neighborhood. When we look out into space and see distant galaxies, we're observing the descendants of that original matter surplus. Each spiral arm, each glowing nebula, each planetary system represents the continuation of an ancient victory of matter over its opposite twin. In the quiet darkness of space, this ancient imbalance continues to shape everything around us, a gentle reminder that sometimes the smallest differences can have the most profound consequences. The very fact that we can contemplate this paradox is itself a testament to the delicate asymmetry that occurred in those first precious moments of cosmic history. Lookback Time Paradox. When you gaze up at the night sky, you're not just looking through space, you're looking back through time. Light from distant galaxies takes billions of years to reach us, creating a cosmic time machine that reveals the universe's ancient past. This creates one of astronomy's most intriguing puzzles. We can see what galaxies looked like long ago, but we can never know what they look like right now. Consider the Andromeda Galaxy, our nearest major galactic neighbor. The light we see from Andromeda tonight began its journey 2.5 million years ago, when early human ancestors were just beginning to use stone tools. The galaxy we observe is a fossil image, preserved in the photons that have traveled across the cosmic dark to reach our eyes. For more distant galaxies, this effect becomes even more profound. The Hubble Space Telescope has captured images of galaxies whose light has been traveling for over 13 billion years, showing us these cosmic islands as they appeared when the universe was less than 1 billion years old. These ancient galaxies look dramatically different from the mature spiral and elliptical galaxies we see nearby. They're smaller, more chaotic, and blazing with the fierce light of star formation. This temporal disconnect creates a fascinating uncertainty. While we can see these distant galaxies as they were in their youth, we can only speculate about their current state. That small, irregular galaxy we observed from billions of years ago might now be a magnificent spiral, complete with elegant arms and a central bulge. Or perhaps it merged with neighboring galaxies, becoming part of a much larger cosmic structure. The paradox deepens when we consider that gravity itself travels at the speed of light. Not only are we seeing the ancient appearance of distant galaxies, but we're also feeling their gravitational influence as it was billions of years ago. The cosmic web of dark matter that shapes the universe's large-scale structure is, from our perspective, frozen in an ancient configuration. Some galaxies we observe may no longer exist at all. Galactic collisions, though rare and slow by human standards, do occur over cosmic timescales. The brilliant galaxy we see in our telescopes might have long since merged with a neighbor. Its identity dissolved into a new, larger cosmic entity. This creates a strange form of cosmic archaeology. Astronomers study galaxies at different distances to understand how they evolve over time, using the universe's own light speed limit as a tool to peer into the past. By comparing nearby galaxies to distant ones, we can piece together the story of galactic evolution. Even though we can never directly observe the same galaxy at different stages of its life. The Lookback Time Paradox reminds us that our view of the universe is fundamentally historical. Every photon that reaches us carries information from the past, creating a constantly updating museum of cosmic history. The most distant galaxies appear to us as they were in their infancy, while nearby galaxies show us more recent chapters in the cosmic story. This temporal layering creates a unique perspective that no other location in the universe could provide. From Earth, we can simultaneously observe the universe at many different ages, from the cosmic microwave background radiation that shows us the universe at just 380,000 years old, to nearby stars that reveal conditions just a few years ago. In this sense, the night sky is not just beautiful, it's a living archive of the universe's long journey through time. Holographic universe paradox. Imagine if everything you experience, every mountain, every cloud, every sensation of depth and dimension were actually information encoded on a distant, flat surface. This mind-bending possibility lies at the heart of the holographic principle, one of theoretical physics' most revolutionary ideas. The concept emerged from studying black holes, those mysterious cosmic entities where gravity becomes so intense that nothing can escape. Physicists discovered something puzzling. The amount of information a black hole can contain depends not on its volume, as we might expect, but on the area of its surface. It's as if all the complexity within the black hole is somehow written on its boundary, like a cosmic library where every book is inscribed on the walls rather than stored on shelves. This discovery led to a startling proposal. If black holes encode their interior information on their surfaces, perhaps our entire universe works the same way. According to the holographic principle, all the information that makes up our three-dimensional reality might actually be encoded on a two-dimensional boundary at the edge of space. Think of it like a hologram on a credit card. The flat surface contains all the information needed to create a three-dimensional image when illuminated properly. Similarly, the holographic universe suggests that what we perceive as depth, volume, and three-dimensional space might be projections from information stored on a cosmic boundary. This doesn't mean our reality is an illusion or somehow less real. Rather, it suggests that three-dimensional space might be a more complex way of organizing and experiencing information that could, in principle, be described in fewer dimensions. The richness of our experience, the warmth of sunlight, the texture of sand, the vastness of space itself would still be genuine, but it might emerge from a more fundamental two-dimensional description. The mathematics supporting this idea comes from string theory and quantum gravity, fields that attempt to unify our understanding of the very large and very small. Researchers have found concrete examples where gravitational theories in higher dimensions are mathematically equivalent to quantum theories on their boundaries. These discoveries suggest that the holographic principle isn't just philosophical speculation. It might be a fundamental feature of how reality works. What makes this paradox particularly intriguing is that it challenges our most basic assumptions about space and dimension. We experience the world as thoroughly three-dimensional, yet the deepest laws of physics might operate according to a two-dimensional logic. This would mean that the universe's complexity and our perception of depth emerge from something more fundamental and simpler. The holographic principle also offers potential solutions to long-standing puzzles in physics, including how information behaves near black holes and how quantum mechanics relates to gravity. If the universe truly operates holographically, it would represent one of the most profound shifts in our understanding of reality since the discoveries of quantum mechanics and relativity. As we continue exploring this cosmic puzzle, we find ourselves contemplating whether the very notion of inside and outside, here and there, might be more fluid than we ever imagined. The holographic universe paradox invites us to consider that reality might be far stranger and more beautiful than our everyday experience suggests. In the gentle darkness of space, where starlight carries information across vast distances, the universe might be writing its entire story on the cosmic horizon, projecting the magnificent three-dimensional theater of existence from a more fundamental, elegant script. This possibility transforms our understanding of space itself, suggesting that even the emptiness between stars might be rich with encoded information, waiting to unfold into the reality we call home. Black hole entropy paradox. In the cosmic hierarchy of disorder, black holes reign supreme. These gravitational giants contain more entropy, a measure of disorder and information, than any other object of comparable size in the universe. This creates a profound paradox that has puzzled physicists for decades and revolutionized our understanding of space, time, and information. Entropy is typically associated with complexity and chaos. A messy room has high entropy, while a perfectly organized one has low entropy. In most systems, more entropy means more space to store information, more ways for particles to arrange themselves, more possibilities for disorder. Yet black holes appear utterly simple from the outside. They can be completely described by just their mass, electric charge, and rotation. The paradox deepens when we consider how entropy typically behaves. If you double the size of a box, you roughly double the amount of entropy it can contain, because entropy usually scales with volume. But black holes break this rule in a spectacular way. Their entropy scales with the area of their surface, not their volume. A black hole twice as wide doesn't contain twice as much entropy. It contains 4 times as much. This discovery emerged from the work of physicists Jacob Bekenstein and Stephen Hawking, who realized that black holes must have temperature and entropy to preserve the fundamental laws of thermodynamics. When matter falls into a black hole, its entropy cannot simply disappear. It must be accounted for somewhere. The only place it can go is onto the black hole's surface. The surface area of a black hole's event horizon, the boundary beyond which nothing can escape, thus becomes a cosmic ledger, recording every bit of information that has ever fallen in. A stellar mass black hole might contain the entropy equivalent to 10 to the power of 77 books, each with 1 billion pages of text. A supermassive black hole could hold information equivalent to 10 to the power of 90 libraries. This creates an almost mystical picture. Black holes as cosmic archivists, storing vast amounts of information on their surfaces while appearing completely featureless to outside observers. Every particle, every photon, every piece of matter that crosses the event horizon leaves its informational signature encoded in the quantum structure of the boundary. The entropy scaling also suggests something profound about the nature of space itself. If the maximum entropy of a region scales with its boundary area rather than its volume, It implies that the three-dimensional space we experience might be somehow projected from information stored on two-dimensional surfaces. This insight contributed to the development of the holographic principle, fundamentally changing how physicists think about reality. What makes this paradox even more intriguing is that it connects the largest objects in the universe to the smallest scales of quantum mechanics. The entropy of a black hole is carried by quantum information at the Planck scale, where space and time themselves become grainy and uncertain. Each tiny region of the event horizon, smaller than an atom, carries exactly one bit of information. Black holes thus serve as cosmic laboratories where the deepest mysteries of physics converge, holding the maximum possible entropy while maintaining perfect simplicity. In the profound darkness surrounding these gravitational titans, information accumulates like cosmic sediment, layer upon layer of reality's deepest secrets encoded in the quantum foam of space-time itself. This paradox reminds us that the universe's most extreme objects often reveal its most fundamental truths. In the gentle mathematics that governs entropy and information, black holes have become teachers, showing us that complexity and simplicity can coexist in ways that challenge our everyday understanding of order and chaos. Heat-death paradox. The second law of thermodynamics tells us a seemingly inevitable story. Entropy always increases, energy becomes less organized, and the universe marches steadily toward a state of maximum disorder, called heat death. Yet when we look around us, we see complexity flourishing everywhere. Stars burning brightly, planets forming intricate weather systems, and life itself organizing matter into increasingly sophisticated forms. This creates one of physics' most profound puzzles. If entropy must always increase, if energy inexorably flows from hot to cold and organized to disorganized, why hasn't the universe already reached its final state of equilibrium? Why is there still usable energy powering the magnificent cosmic dance we observe today? The answer lies in understanding that the universe is not a closed box with fixed contents. Instead, it's an expanding system where new space constantly comes into existence, providing room for entropy to grow without immediately consuming all available energy. As the universe expands, it becomes increasingly dilute, but this expansion itself creates opportunities for new forms of organization to emerge. Consider a star like our Sun. It represents a highly organized, low-entropy system that converts hydrogen into helium, releasing tremendous amounts of energy in the process. According to the heat-death scenario, this should be impossible. Energy should have already spread out evenly throughout space. Yet stars continue to shine because the universe's expansion allows gravity to collect matter into dense regions where nuclear fusion can occur. The cosmic microwave background radiation provides another clue. This ancient light, cooled by billions of years of cosmic expansion, represents the afterglow of the Big Bang. As the universe expanded, this radiation stretched and cooled, its entropy increasing dramatically. Yet this same expansion created the temperature differences necessary for the first stars and galaxies to form. Cosmic expansion acts like a cosmic refrigerator, constantly creating new cold space into which hot objects can radiate their energy. This process allows the universe to maintain useful energy gradients even as its total entropy increases. The expansion provides a constantly growing canvas on which complexity can paint itself. Dark energy adds another layer to this paradox. This mysterious force accelerates cosmic expansion, seemingly working against gravity's tendency to create the dense regions where stars and galaxies form. Yet dark energy's influence ensures that the universe continues expanding, maintaining the conditions necessary for ongoing stellar evolution and energy production. The formation of black holes also plays a crucial role. When massive stars collapse, they create regions of space-time with enormous entropy capacity. Black holes can absorb matter and energy, while storing vast amounts of entropy on their surfaces, effectively serving as cosmic entropy reservoirs that allow other regions of space to remain organized. Even biological evolution participates in this cosmic story. Life creates local decreases in entropy by organizing matter into complex structures, but it does so by increasing entropy elsewhere through heat production, waste, and the consumption of low-entropy energy sources like sunlight. The heat-death paradox ultimately reveals that entropy increase and cosmic organization are not contradictory forces, but complementary aspects of the universe's evolution, working together across the vast scales of space and time. The universe has found elegant ways to satisfy the demands of thermodynamics, while still allowing for the emergence of stars, planets, and the remarkable complexity we observe today. In the gentle interplay between expansion and gravity, between order and disorder, the cosmos continues its slow dance toward ultimate equilibrium, while nurturing islands of complexity and beauty. This paradox reminds us that even the most fundamental laws of physics can manifest in ways that create rather than destroy, that build rather than merely tear down. Quantum Suicide Paradox. The quantum suicide paradox presents one of the most unsettling thought experiments in modern physics, suggesting that, from your own perspective, you might be immortal in the strangest possible way. This paradox emerges from the many worlds interpretation of quantum mechanics, where every quantum measurement splits reality into multiple parallel branches. Imagine you're part of a quantum experiment, where your survival depends on the random decay of a radioactive atom. In classical physics, you'd have a 50% chance of survival each time the experiment runs. But according to the many worlds interpretation, something far more peculiar occurs. At each moment when the atom might decay, reality branches into two parallel universes, one where you survive and one where you don't. Here's where the paradox becomes deeply strange. While observers in the branch where you die would witness your demise, your consciousness can only continue to exist in the branches where you survive. From your subjective perspective, you would experience an unbroken chain of survival, no matter how unlikely the odds become. Even if the experiment were repeated thousands of times, you would always find yourself in the surviving branch, because that's the only branch where you exist to observe the outcome. This creates a form of quantum immortality that applies only to the experiencing subject. Other observers would see you die in some branches and survive in others, following the normal statistical predictions of quantum mechanics. But your own conscious experience would trace an increasingly improbable path through reality, jumping from one surviving branch to another. The paradox extends beyond thought experiments. Some interpretations suggest that this principle might apply to all life-threatening situations involving quantum events, which at the microscopic level includes nearly everything. Your consciousness might be constantly navigating through a maze of parallel realities, always finding itself in the branches where survival is possible. This raises profound questions about the nature of conscious experience and identity. If your awareness automatically selects for survival across parallel worlds, are you experiencing the real universe? Or are you following an increasingly unlikely path through quantum possibility space? The paradox suggests that your personal timeline might be fundamentally different from the statistical average that other observers would measure. The quantum suicide paradox also highlights the strange relationship between observation and reality in quantum mechanics. While the physical world might branch and split according to quantum probabilities, conscious experience appears to follow a single, continuous thread through this multiverse. This suggests that consciousness itself might play a unique role in determining which version of reality we experience. Critics argue that consciousness doesn't require quantum mechanics to explain its continuity, and that the paradox confuses subjective experience with physical processes. Yet the paradox remains a powerful illustration of how quantum mechanics challenges our basic assumptions about death, survival, and the nature of personal identity across multiple realities. Whether or not quantum immortality actually occurs, the paradox invites us to consider how our experience of reality might be shaped by the fundamental quantum nature of existence itself. In the quiet spaces between quantum measurements, consciousness might be writing its own story across the infinite pages of parallel worlds, always choosing survival, always continuing the narrative of awareness through the vast library of possible realities. Pauli Exclusion and Paradox. Deep within every atom lies one of nature's most fundamental prohibitions. The Pauli exclusion principle states that no two identical particles can occupy the same quantum state simultaneously. This seemingly simple rule creates a profound paradox. How does this microscopic prohibition give rise to all the structure and stability we observe in the universe? Consider the electrons orbiting an atomic nucleus. Without the exclusion principle, all electrons would crowd into the lowest energy state, closest to the nucleus. Atoms would collapse into incredibly dense points, and the familiar chemistry that creates molecules, crystals, and life itself would be impossible. Instead, electrons are forced to occupy different energy levels, creating the layered structure of electron shells that determines an atom's chemical properties. This exclusion creates what physicists call degeneracy pressure, a force that emerges purely from quantum mechanical restrictions rather than from any physical interaction. When particles are squeezed together, the exclusion principle prevents them from occupying the same state, creating an outward pressure that resists further compression. This quantum pressure is responsible for the stability of ordinary matter under extreme conditions. The paradox becomes even more striking when we consider stellar evolution. When a massive star exhausts its nuclear fuel, gravity tries to crush it into infinite density. But the exclusion principle intervenes dramatically. First, electron degeneracy pressure halts the collapse, creating a white dwarf star roughly the size of Earth, but containing the mass of our Sun. The star becomes supported not by heat or nuclear reactions, but by the quantum mechanical requirement that electrons maintain their individual identities. For even more massive stars, this quantum resistance continues in stages. When electron degeneracy pressure finally fails, neutron degeneracy pressure takes over, creating neutron stars, city-sized objects containing more mass than our Sun, held up entirely by the exclusion principle applied to neutrons. These cosmic lighthouses spin hundreds of times per second, their entire structure maintained by quantum mechanical prohibition. The exclusion principle also explains why we don't fall through solid objects. When you sit in a chair, you're supported not by some mechanical resistance, but by the quantum mechanical fact that the electrons in your body cannot occupy the same states as the electrons in the chair. The sensation of solidity emerges from this fundamental quantum rule. In the realm of chemistry, the exclusion principle determines how atoms bond with each other. The unique arrangement of electrons in different energy levels creates the periodic table structure, with each element's chemical behavior determined by how its electrons are forced to arrange themselves according to Pauli's prohibition. The paradox deepens when we realize that this principle applies only to fermions, particles with half-integer spin like electrons, protons, and neutrons. Their counterparts, bosons, face no such restriction and can pile into the same quantum state indefinitely. This fundamental difference in behavior shapes the entire architecture of matter and energy in our universe. Through this simple prohibition, quantum mechanics creates the scaffolding upon which all complex structure rests, transforming a universe that might otherwise collapse into uniform density into the rich, layered reality we inhabit. No boundary paradox, Hartle-Hawking. In the deepest questions of cosmology lies a puzzle that challenges our most basic concepts of time and causality. The Hartle-Hawking no-boundary proposal suggests that the universe might have no beginning in the traditional sense, yet somehow time and causality emerge from a state that transcends our usual understanding of nothing and something. Traditional Big Bang cosmology faces a fundamental problem at the moment of creation. As we trace the universe backward through time, we encounter a point where our physics breaks down, a singularity where density becomes infinite and the laws of nature cease to apply. This creates the uncomfortable question: what came before the Big Bang, and what caused it to occur? The Hartle-Hawking proposal offers an elegant but mind-bending solution. Instead of imagining the universe beginning at a specific moment in time, they suggest that time itself gradually emerges from a timeless quantum state. In their model, the universe has no boundary in time, much like the surface of a sphere has no edge. Just as you can travel around Earth's surface without ever reaching a beginning or end, you might trace the universe's history without ever finding a first moment. This timeless origin involves a mathematical transformation, where time becomes imaginary in the technical sense, not fictional, but described using complex numbers that allow smooth transitions between different types of geometry. In this primordial state, the distinction between time and space dissolves. The universe exists in a quantum superposition of all possible geometries, with no definite beginning or definite sequence of events. From this timeless quantum soup, classical time emerges gradually through a process similar to phase transition. Just as water vapor condenses into liquid droplets, the universe's quantum geometry condenses into the familiar spacetime we experience today. Time becomes real, and causality becomes meaningful. But these emerge as collective properties rather than fundamental features. The paradox challenges our deepest intuitions about cause and effect. In our everyday experience, every event has a cause that precedes it in time. But if time itself emerges from a timeless state, the usual notion of causality becomes meaningless at the universe's origin. The universe doesn't begin because something caused it to begin. Rather, it exists because existence is the most probable outcome of the underlying quantum geometry. This proposal also addresses the puzzle of why the universe appears fine-tuned for complexity and life. Rather than requiring specific initial conditions, the no-boundary proposal suggests that universes with properties suitable for structure formation are simply more probable outcomes of the quantum creation process. The universe we observe emerges naturally from the mathematical landscape of possible quantum geometries. The no-boundary paradox represents a profound shift in how we think about cosmic origins. Instead of asking what caused the Big Bang, we might ask how causality itself emerged from a deeper, more fundamental reality where questions of before and after have no meaning. In this view, the universe becomes self-creating in the deepest possible sense, neither requiring an external cause nor springing from absolute nothingness, but emerging from the timeless mathematical possibilities inherent in quantum geometry itself. False vacuum paradox. Our universe might be living on borrowed time, existing in a state that appears stable but could spontaneously decay at any moment, transforming all of reality in the process. This unsettling possibility emerges from the false vacuum paradox, which suggests that what we perceive as empty space might actually be a temporary metastable state, waiting to collapse into something entirely different. To understand this paradox, imagine a ball resting in a shallow valley on a hillside. The ball appears stable, but it's not in the lowest possible position. If disturbed enough, it could roll down to a much deeper valley below. The false vacuum hypothesis suggests that our universe's fundamental energy state might be similar, apparently stable, but not at the absolute minimum possible energy level. The Higgs field, which gives particles their mass, provides the most concrete example of this phenomenon. Current measurements suggest that the Higgs field might exist in a metastable state, like water that remains liquid below its freezing point. Under normal conditions, this false vacuum appears perfectly stable, but quantum fluctuations could potentially trigger a phase transition to the true vacuum state. If such a transition occurred, it would begin at a single point in space and expand outward at the speed of light, creating a bubble of true vacuum within our false vacuum universe. The boundary of this bubble would be invisible and undetectable until it reached us, at which point the fundamental properties of space itself would change instantaneously. This transformation wouldn't simply destroy matter. It would rewrite the basic rules governing how particles interact. The masses of electrons, protons, and neutrons might change dramatically. The strength of electromagnetic and nuclear forces could shift. The very atoms that make up your body might become impossible to exist in the new vacuum state. The paradox becomes even more intriguing when we consider that vacuum decay could have already occurred somewhere in the universe. A bubble of true vacuum might be expanding toward us right now, but we would have no way of detecting it until it arrived. The change would appear to move at light speed, giving us no advance warning and no opportunity to observe its approach. Yet this catastrophic possibility coexists with remarkable stability. If the false vacuum were truly unstable, quantum fluctuations would have triggered the decay long ago during the universe's hot, energetic early phases. The fact that we exist suggests either that our vacuum is truly stable, or that the decay rate is so incredibly slow that it's effectively impossible over cosmic timescales. Some cosmological models suggest that inflation itself might have been driven by false vacuum decay. The rapid expansion of space during the universe's first fraction of a second could represent a transition from an earlier false vacuum state to our current one. This raises the intriguing possibility that vacuum decay isn't always destructive. It might be the mechanism that created the conditions necessary for our existence. The false vacuum paradox highlights the precarious nature of what we consider fundamental and permanent. Even the emptiness of space, which seems like the most basic possible state, might harbor hidden instabilities that could reshape reality at the deepest level. Einstein's box paradox. In the quantum world, measuring one property of a system can mysteriously affect what we can know about other properties, even when the system is completely isolated from outside influences. Einstein's box paradox illustrates this strange relationship between measurement and uncertainty, challenging our intuitive understanding of how isolated systems should behave. Imagine a perfectly sealed box containing a single photon of light. According to quantum mechanics, if we measure the photon's energy very precisely, we unavoidably increase our uncertainty about when that measurement occurred. Conversely, if we determine the exact time of measurement, we lose precision in knowing the photon's energy. This trade-off, described by Heisenberg's uncertainty principle, seems to suggest that the act of measurement somehow disturbs the system. Einstein found this deeply troubling. How could measuring one property affect knowledge of another property in a completely closed system? The box is sealed. Nothing gets in or out. The measurement apparatus is external to the box. Yet, quantum mechanics insists that gaining precise information about energy necessarily creates uncertainty about time, and vice versa. The paradox deepens when we consider what measurement actually means in this context. To measure the photon's energy precisely, we might allow it to escape the box at a precisely controlled time and analyze it with external detectors. But the very act of opening the box to let the photon out necessarily involves the box's mass changing as the photon escapes. And this mass change affects the box's gravitational field in a way that's coupled to time. Einstein realized that this coupling is unavoidable. To measure the photon's energy precisely, we need to know exactly how much mass energy left the box. But measuring this mass change precisely requires us to monitor the box's position very carefully over time, which introduces quantum uncertainty into when exactly the photon escaped. The measurement process inevitably entangles time and energy measurements. This reveals something profound about the nature of information in quantum systems. The uncertainty principle isn't just a limitation of our measuring instruments. It's a fundamental feature of how information itself behaves in quantum systems. Even in perfect isolation, the quantum state of a system contains complementary aspects that cannot all be known simultaneously. The paradox also illuminates the deep connection between quantum mechanics and relativity. The relationship between energy and time, uncertainty, mirrors the relationship between mass and space-time curvature in Einstein's general relativity. Measuring energy precisely enough to violate the uncertainty principle would require measurements precise enough to detect quantum gravitational effects. Modern interpretations suggest that Einstein's box paradox reveals the unavoidable relationship between information and physical processes. You cannot extract information from a quantum system without interacting with it, and this interaction necessarily affects what other information can be simultaneously extracted. The box remains isolated, but the process of learning about its contents requires connecting it, however briefly, to measuring devices. The paradox thus highlights one of quantum mechanics' most counterintuitive features. In the quantum world, information itself has physical consequences, and the act of knowing necessarily changes what can be known about related properties. Unitarity Paradox. One of physics' most profound puzzles emerges at the intersection of quantum mechanics and gravity, where the fundamental principle of information conservation appears to clash with the behavior of black holes. The Unitarity Paradox asks a deceptively simple question. If quantum mechanics requires that information can never be truly destroyed, what happens to the information that falls into a black hole? In quantum mechanics, unitarity is a sacred principle. It states that the total amount of information in any quantum system must remain constant over time. Information can be scrambled, encoded, or transformed beyond recognition, but it can never vanish completely. This principle underlies all quantum processes, from the decay of radioactive atoms to the complex calculations performed by quantum computers. Black holes seem to violate this fundamental rule. When matter falls past a black hole's event horizon, it appears to disappear forever from the perspective of outside observers. The information contained in that matter, every detail about its quantum state, its history, its relationships with other particles, seems to be permanently lost to the universe. This creates a direct contradiction with quantum mechanics' most basic requirements. Stephen Hawking deepened this paradox with his discovery that black holes emit radiation. This Hawking radiation causes black holes to slowly evaporate, eventually disappearing completely. But the radiation appears to be perfectly thermal, carrying no information about what fell into the black hole originally. If the black hole evaporates completely while emitting only random thermal radiation, the information that fell in seems to be permanently destroyed. This information destruction would represent a fundamental breakdown of quantum mechanics. It would mean that pure quantum states could evolve into mixed states, that reversible processes could become irreversible, and that the universe could lose information about its own history. Such violations would undermine the entire mathematical framework of quantum theory. Several potential solutions have emerged, each with profound implications for our understanding of reality. The holographic principle suggests that information falling into a black hole is actually encoded on its surface, never truly entering the interior. From this perspective, information is preserved, but in a form so scrambled that it appears to be lost. Another possibility involves quantum entanglement between particles inside and outside the black hole. As the black hole evaporates, the entanglement between internal and external particles might gradually transfer information back to the outside universe through the Hawking radiation, though in a highly encoded form. Some physicists propose that black hole interiors don't exist as separate regions of spacetime, but are instead quantum mechanical illusions created by the entanglement structure of the external region. In this view, information never actually crosses the event horizon, but remains accessible to outside observers through quantum correlations. The most radical solution suggests that spacetime itself might be emergent from quantum information. If space and time arise from underlying quantum entanglement patterns, then the apparent destruction of information in black holes might reveal deep truths about the fundamental nature of reality itself. The Unitarity Paradox remains unsolved, representing one of the most important outstanding problems in theoretical physics. Its resolution may require a complete revolution in how we understand the relationship between quantum mechanics, gravity, and information. Observer effect paradox. In the quantum realm, the simple act of looking appears to fundamentally alter reality itself. The observer effect paradox suggests that observation doesn't just reveal properties that were already there, it actually brings those properties into existence through the very act of measurement. This challenges our most basic assumptions about the relationship between knowledge and reality. Consider the famous double-slit experiment, where individual particles of light or matter are fired at a barrier containing two narrow openings. When no one observes which slit the particle passes through, it behaves like a wave, somehow going through both slits simultaneously and creating an interference pattern on a detector screen. But the moment we place a detector to observe which slit the particle uses, the wave-like behavior vanishes, and the particle behaves as if it went through only one slit. This suggests something profound. The particle's behavior depends not on its physical interaction with measuring devices, but on whether information about its path becomes available to an observer, even if the measuring device is present but turned off, or if its data is erased before anyone can read it, the wave-like behavior returns. It's as if the universe responds to the possibility of knowledge rather than to physical intervention. The paradox deepens when we consider delayed choice experiments. In these setups, the decision of whether to observe the particle's path can be made after the particle has already passed through the slits, but before it hits the detector screen. Remarkably, this future decision seems to retroactively determine whether the particle behaved as a wave or particle while passing through the slits. Some interpretations suggest that consciousness itself plays a fundamental role in quantum mechanics. In this view, the universe exists in a superposition of all possible states until a conscious observer makes a measurement. at which point reality crystallizes into a single definite outcome. This would mean that consciousness is not just a passive witness to reality, but an active participant in its creation. Other interpretations avoid invoking consciousness by focusing on the physical process of information creation. When a quantum system becomes entangled with its environment in a way that creates a permanent record, the system's quantum coherence is destroyed through a process called decoherence. This doesn't require a conscious observer, just any interaction that creates lasting information about the system's state. The many worlds interpretation offers another perspective. Observation doesn't change reality, but reveals which branch of the multiverse we happen to occupy. Every possible outcome occurs in parallel universes, and observation simply determines which branch our consciousness experiences. Modern quantum experiments have pushed the observer effect to its limits. Researchers have demonstrated quantum behavior in increasingly complex systems, from individual atoms to large molecules containing hundreds of atoms. They have also shown that the observer effect operates even when the observer is an automated detector with no human involved. The observer effect paradox reveals the strange intimacy between knowledge and reality in the quantum world. Whether through consciousness, information creation, or parallel universes, the act of knowing appears to be woven into the fundamental fabric of existence itself, making observers not just witnesses to reality, but partners in its ongoing creation. Quantum Cheshire Cat Paradox. In Lewis Carroll's tale, the Cheshire Cat could vanish while leaving only its grin behind. Quantum mechanics suggests something equally strange might be possible. Particles can be separated from their own properties, existing in one location while their characteristics appear somewhere else entirely. This bizarre possibility lies at the heart of the Quantum Cheshire Cat Paradox. The paradox begins with neutrons, particles that carry both mass and magnetic properties. In classical physics, these attributes are inseparable. Wherever the neutron goes, its magnetism follows. But quantum mechanics allows for a more surreal possibility. Through careful manipulation of quantum states, researchers have found ways to send neutrons through one path in an interferometer, while their magnetic properties travel through a different path. This separation is achieved through a technique called weak measurement, where the interaction between the measuring device and the quantum system is so gentle that it barely disturbs the particle's quantum state. By making measurements that are just strong enough to extract information but too weak to fully collapse the quantum wave function, physicists can determine where different properties of a particle are most likely to be found. The results are counterintuitive. When neutrons enter the interferometer in a carefully prepared quantum state, weak measurements reveal that the particles themselves preferentially take one path, while their magnetic moments primarily follow the other path. The neutron and its magnetism become quantum mechanically divorced, existing in the different regions of space while remaining part of the same quantum system. This separation isn't just theoretical. Experimental verification has confirmed that the phenomenon occurs exactly as quantum mechanics predicts. The neutron's particle-like properties and its magnetic field can indeed be detected in different locations within the interferometer, as if the Cheshire Cat's body went one way while its grin went another. The paradox challenges our classical intuition about the relationship between objects and their properties. In everyday experience, properties are bound to their objects. A red ball cannot be somewhere else from its redness, and a magnetic compass needle cannot be separated from its magnetic field. But quantum mechanics reveals that this binding is not as fundamental as we might expect. The quantum Cheshire Cat effect has practical implications for quantum technology. It suggests new ways to manipulate quantum information, potentially allowing for more sophisticated quantum computing protocols and communication schemes. If properties can be routed independently of particles, this might enable novel forms of quantum information processing. The paradox also raises deep philosophical questions about the nature of objects and properties. If a neutron can exist separately from its magnetism, what does it mean to say that the magnetism belongs to the neutron? Are properties fundamental aspects of particles? Or are they more like quantum information that can be stored and transferred independently? Some interpretations suggest that the Cheshire Cat effect reveals the holistic nature of quantum systems. Rather than thinking of particles as discrete objects with attached properties, we might need to view quantum systems as unified wholes, where particle-like and property-like aspects can manifest in different spatial locations, while remaining part of a single, non-local quantum entity. The quantum Cheshire cat paradox thus invites us to reconsider the most basic categories we use to understand reality, suggesting that the quantum world is far stranger and more flexible than our classical concepts can easily accommodate. Time-Symmetry Paradox. The fundamental laws of physics display a curious symmetry. They work equally well whether time flows forward or backward. Yet our universe shows a clear direction to time's arrow, with causes preceding effects and entropy increasing relentlessly. This creates the Time-Symmetry Paradox. If the basic rules are symmetric, why does reality appear so decisively asymmetric? Consider the equations that govern motion, electromagnetism, and even quantum mechanics. These mathematical relationships remain valid if we replace time with negative time, effectively running the universe backward. A planet orbiting the sun follows the same gravitational laws whether time moves forward or backward. Electromagnetic waves propagate according to the same principles in both temporal directions. Even at the quantum level, the Schrödinger equation maintains its form under time reversal. This symmetry suggests that physics cannot distinguish between past and future at the most fundamental level. If we could record a movie of particles colliding and then play it backward, the reversed version would show events that are equally consistent with physical law. The microscopic world appears to be temporally neutral, with no preferred direction for time's flow. Yet our everyday experience tells a dramatically different story. We remember the past, but not the future. Eggs break when dropped, but never spontaneously reassemble. Heat flows from hot objects to cold ones, never the reverse. Entropy increases, disorder spreads, and the universe appears to have a definite direction through time. The resolution to this paradox lies in understanding the role of initial conditions and statistical mechanics. While individual particle interactions are time-symmetric, the collective behavior of vast numbers of particles can create irreversible processes. When billions of molecules move randomly, their statistical behavior produces the one-way flow we observe as entropy increase. The key insight involves the concept of thermodynamic equilibrium. Starting from special, highly ordered initial conditions, like all the gas molecules in a room being confined to one corner, the system will naturally evolve toward maximum disorder. But while the forward evolution toward equilibrium is highly probable, the reverse process, where molecules spontaneously organize themselves into a corner, is so improbable as to be effectively impossible. Cosmology provides another perspective on time's arrow. The universe began in an extremely low entropy state. The Big Bang represented maximum order, with matter and energy distributed very smoothly. As the universe expanded and evolved, gravity allowed matter to clump together, creating the complex structures we see today, while simultaneously increasing the overall entropy of the system. Black holes play a crucial role in this cosmic story. They represent maximum entropy configurations, serving as the universe's ultimate entropy repositories. The formation of black holes is irreversible on cosmic scales, providing a clear direction to time's arrow throughout the universe's evolution. Quantum mechanics adds another layer to the paradox. While quantum equations are time-symmetric, the process of quantum measurement appears to break this symmetry. Measurements collapse quantum superpositions into definite outcomes, creating information that provides a record of the past, but not the future. The Time-Symmetry Paradox ultimately reveals that time's arrow emerges from statistical and cosmological properties, rather than from fundamental physical laws. The universe's temporal direction arises from its history and initial conditions, creating the asymmetric flow of time within a framework of symmetric physical principles. Cosmic Censorship Paradox. Deep within Einstein's theory of general relativity lurks a disturbing possibility: the existence of naked singularities, points where space-time curvature becomes infinite without being hidden behind an event horizon. The Cosmic Censorship Paradox asks whether the universe protects us from directly observing these extreme gravitational anomalies, or whether they can exist in plain sight. Singularities represent the ultimate breakdown of our physical theories. At these points, density becomes infinite, space-time curvature becomes infinite, and the normal laws of physics cease to apply. We know that singularities exist at the centers of black holes, but they're safely hidden behind event horizons, boundaries beyond which nothing, not even light, can escape to reach outside observers. The cosmic censorship hypothesis proposed by Roger Penrose suggests that nature abhors naked singularities. According to this conjecture, any process that creates a singularity will also create an event horizon around it, preventing outside observers from witnessing the singular behavior. This would mean that while singularities might exist, they would always remain clothed by the cosmic equivalent of a modesty screen. But general relativity permits solutions where naked singularities could theoretically form. Computer simulations show scenarios where the gravitational collapse of certain matter configurations might create exposed singularities visible to distant observers. These naked singularities would represent regions where infinite spacetime curvature could be directly observed and studied. The existence of naked singularities would create profound problems for physics. Unlike black hole singularities, which are causally disconnected from the rest of the universe, naked singularities could send signals to outside observers. Information from a region of infinite curvature might propagate throughout spacetime, potentially allowing effects to precede their causes and creating violations of causality. Such violations would make the universe unpredictable in principle. If naked singularities exist, then regions of infinite curvature could emit arbitrary signals, making it impossible to predict the future evolution of spacetime, even with perfect knowledge of initial conditions. The universe would become fundamentally unpredictable near these exposed singularities. Modern research suggests that cosmic censorship might not be absolute, while strong cosmic censorship, which prevents any information from escaping singularities, appears to hold in most cases weak cosmic censorship, which only prevents the formation of naked singularities from realistic initial conditions, might be violated under certain circumstances. Quantum effects add another layer to the paradox. When quantum mechanics is taken into account, the behavior near singularities becomes even more complex. Some theories suggest that quantum processes might actually prevent the formation of naked singularities by creating event horizons before singularities can become exposed. String theory and other quantum gravity theories propose that spacetime itself becomes discrete at the smallest scales, potentially eliminating singularities altogether. In these theories, what appears to be a singularity in classical general relativity might actually be a highly curved but finite region of quantized spacetime. The cosmic censorship paradox represents more than just a technical problem in general relativity. It touches on fundamental questions about the predictability and causality of the universe. If naked singularities exist, they would represent windows into regions where our current physics breaks down completely, offering glimpses of whatever deeper theory might replace general relativity in the extreme gravitational regime. Whether cosmic censorship protects us from these extreme phenomena, or whether naked singularities lurk in the cosmos, remains one of the deepest unsolved problems in gravitational physics. I hope you enjoyed this video, and if you're still awake, there's another cosmic journey waiting for you right here on the screen. One I'm sure you'll love. See you in the next video, and until then, sweet dreams among the stars.